Okay, are we good? Are we good? Okay, I'm gonna get started. Hi everybody. Thank you guys for coming to Apache Iceberg SF Meetup today. I'm Chan. I'm the dev role at Daft. We have a very exciting night. We have Connor to start off from Daft. He will be talking about building S3 table support. And then we have Arshan from Gravy. He's right here in the front. Can you stand up and say hi? Hi. And then next we have Emery from Dremio. Can you stand up and say hi? Hi. And then lastly, we have Ani Ruth from Databricks. Hi. Great. I just did the agenda. There's the agenda. We'll have a 5-minute break in between Arsham and Emery. And then while you're here, subscribe to the DAF Luma calendar. We plan on holding events every month in this lovely space now that the sun doesn't set early. Look at the view. It's beautiful. And then lastly, we're hiring, so if any of these roles sound like you, or if you are interested in what we're doing, come email us. That's my spiel. Just quick raise of hands. How many people know about Iceberg? Okay, great. As you should, as you should. How many people are using Iceberg? Okay, awesome, awesome. How many people know what Daft is? Okay, great. Not a whole lot, which is good because now we're going to hand it off to Connor, who will teach us all about Daft. Yeah, I lost my slide. It's right here. About that. Of course. Of course.
I laughed. Hello. Hello, everyone. My name is Connor. I work at Eventual, and today I'll be talking about how we support S3 tables in Daft. A little background on myself. I live in Seattle. Is anyone here from Seattle or visiting from Seattle? Welcome, welcome. We might have been on the same flight. So in Seattle, I'm really into cycling, climbing, mountain biking, pretty much all the mountain sports. Super nice out there. And what brought me out there was Amazon. I graduated in 2019. I joined Amazon. I worked for CloudWatch Logs for several years. Many of you guys use Logs Insights. So yeah, it's a good service. So I worked on that for a few years, and then I worked on the particle query language. That's like a SQL dialect that's used on Redshift. It's used on QLDB, DynamoDB, and other AWS services. And that led me to Eventual, where I work on Daft SQL, and recently I've been working on our catalog integrations. And yeah, so pretty much when it comes to the catalog integration stuff, like Daft has really, really good I/O for tables. You can like read and write a lot of these open table formats. And so by building these catalog integrations, we're able to have higher level abstractions over that data frame I/O, and it kind of unlocks a lot of possibilities with our APIs. The basic agenda of this talk is going to be, you mind turning it down to the TV? So the basic agenda of this talk is I'm going to say like what is or like are S3 tables and like what problems do they solve, go over some examples of like why they're useful, and then we'll figure out how do S3 tables relate to Iceberg tables. Then I'll show you like how to set things up and how we can actually start using them, and then how you can use them with Daft. I'll demonstrate how to like read and write these tables with Daft. And with the setup and the AWS getting started, we're going to run into some problems. And so we'll like work through those together. And then at the end, I'll show like what's next for Daft and S3 tables, because we'll see there's things that we're going to be able to do that we know about that we can improve upon in our upcoming releases. So the first thing is, what is our S3 tables? So yeah, and why am I saying is R? Because there's more to this. So like we're going to dig into it. So first, S3 tables is a new AWS service. We'll see in the SDK, S3 tables is a different service than S3. It's its own thing. And it's offered alongside S3 storage. When you create a bucket, you can create a table bucket. And these table buckets are optimized for storing Iceberg tables, which is pretty nice. Check a box and you get better hardware for you. And then S3 tables supports Apache Iceberg tables. And there's something we need to dive into here. So we'll talk about like what exactly is meant by supporting Iceberg tables and supporting Iceberg in general. And then a very important thing is S3 tables is a service with its own API, but this API is not the Iceberg REST protocol. And we'll talk about what problems that has, but what we can do and how we can integrate with other AWS services like Late Formation and Glue, and we can make it Iceberg REST compatible. So what does S3 tables solve for us? Well, first, it reduces a lot of complexity because you can just, the click of a button, create a bucket, and you already have like a hosted catalog service. You have your storage. You have access management with IAM. There's a lot of things that it does for you. And like all you're doing is just creating a bucket. So it's really useful. The other thing is it has like managed maintenance jobs. So you can just like, one API, put bucket maintenance job, and you have automatic compaction. You don't have to set up your own infrastructure. It's just all through S3 tables. And then S3 tables is decoupled from the table format. It sounds strange because like I'm only talking about Iceberg. It's just Iceberg, Iceberg, Iceberg. But you'll see like in the API, there's room so that like say Iceberg were to like evolve to a new version and there's some performance improvements or some kind of setup that's better for your workloads through these like managed jobs, you could be able to migrate to that new thing without ever changing your stack because the bytes are just rewritten for you underneath. And then finally, these S3 tables make it really easy to integrate with other AWS services. So check a few boxes and you can use Redshift, you can use Athena, you can write some particle queries. Okay, so how do S3 tables relate to Iceberg tables? We can think of an S3 table as like a logical construct. It's decoupled from the actual bytes. So like S3 table is just a name that we assign to a bunch of data stored somewhere. But then if we peek inside, we'll see it's just an Iceberg table. And so Apache Iceberg is the actual like physical format of all the, like the files and bytes inside of this bucket. And since S3 tables use Iceberg as the actual storage format, we should be able to just like read it with all of our existing tools without too much work. So let's look at our favorite tool, Daft. If no one here is, or if you are not familiar with Daft, it's an engine for data engineering, analytics, and ML AI. I think what's really cool about Daft is it has a Python data frames API, which is like quite ergonomic and really nice, easy to use, but also has a SQL API. And so depending on like your interest, background, whatever you like, or your current setup, you can use both. You can take advantage of it. That's also pretty cool because it runs lightweight locally and like can often outperform DuckDB, but it also seamlessly can run on a distributed cluster and integrates well with Ray. So it's a super cool engine, but can it read S3 tables? So, like I was saying, Daft has very good I/O capabilities when it comes to Iceberg. So the short answer is yes, we can read S3 tables, but how do we do that? What we need to do is map that logical construct of an S3 table to the actual Iceberg files. So here I have my setup, and this is the S3 table service, and there's the Daft engine. When I get some identifier, like, select star from my table, I need to go look up, like, where is my table? What is it? And so a catalog is the service that tells us, given this, path, here are the bytes for it. For Iceberg, that means go find this metadata file. Go find the most recent metadata file. Once you've given your identifier, you get back your metadata file, and that has all of the details of how to go find a bunch of S3 objects and start crunching. Okay, so we should be able to read them if we can get our hands on this metadata file. But I need to set some stuff up first. So now I'm going to walk through AWS's like getting started tutorial, and we'll figure out how to like create one of these buckets, create a table. And our goal here is to upload a Parquet file. So the first thing is we go to the CLI and we see AWS S3 tables, create table bucket. This is a new service. You have to update your CLI, and it's not under S3. Next thing is we create a namespace. So when you guys work with Iceberg, once you have a catalog or once you have a place to put the data, then you have to create a namespace and then you get your table in there. So I just create a namespace. It's just called demo. And now we're ready to create a table. To create a table, I have to give it the table bucket ARN, so the table bucket I just made. I have to give it that namespace demo. And then I'm naming my table points. And the format is Iceberg. So like maybe one day that'll say Iceberg 3 or Iceberg 4, or maybe it might say something else. But you specify the format because it might be stored as something different. And then I give it an Iceberg schema. For this one, sorry guys in the back, but there's 3 fields, X, Y, and Z. We have a Boolean, we have a number, and we have a string. We can do anything with those. So let's try to insert a Parquet file. So I go back to the CLI and I go AWS S3 tables and do insert into, give it my table ARN, I give it my file. It's like super easy. But of course, this does not work. It's because I wrote insert. I should write put. Everyone knows that's the AWS verb. It's not insert, insert SQL. No, I'm just teasing. So if we go to the APIs, we'll go look at put, and we'll see none of these APIs have anything to do with actually like putting data into that table. It's all managing metadata. It's all, deleting things, creating things, namespaces, putting policies. So there's no API to insert data. So I keep going through the tutorial and I'm like, okay, how am I supposed to do this? And then it just like jumps to this. And it's a Spark, like it's a Scala REPL with Spark, and everything's already all configured. And I'm following along and it just says like we can access and populate the table in many different ways. For testing purposes, we've installed Apache Spark, then invoke the Spark shell with quote command line arguments. But I'm like, what command line arguments? Like it's pretty, I just want to upload my file. Getting to this point is not trivial. Yeah, so one does not simply just install Spark and invoke it. It doesn't work that easily. So yes, we're gonna figure out what these mysterious command line arguments are. So I went to ChatGPT. So I found a different I went to a different blog post and what I saw were all these arguments. So it's just a bunch of configuration and you'll see these like probably Maven path stuff. And it's pointing us to this like jar that has a bunch of logic to be able to fetch this metadata and so on and so forth. And when I tried to follow this tutorial, I had some issues where I just kept getting like class not found and add another dependency and go class not found. And you're like, if you depend on that jar, why aren't you pulling it transitively? But whatever. It took me too long. Someone smarter than me will figure it out. But another thing I noticed is the bucket that I created was like called pond, but here it's called like Spark catalog. So when I first got this thing running, I was like trying to like say, catalog.schema.table, and it like renamed my catalog. I was kind of confused by that. And then I realized I don't think I can connect to multiple S3 buckets if they're all just going to be named Spark catalog. So I figured there's some room for improvement here. And also, what about Python? Most of us, well, a lot of us use Python, and I didn't really want to be dealing with all these jar issues. And I'm just trying to upload a file, so figure out what we can do. Yeah, I just created all of these resources, and I still can't upload stuff. So now what? So we're going to explore some alternatives. And this was cool. This is in like one of the benefits of S3 tables is check a few boxes, integrate with all the different AWS services. But I don't really want to start using Athena and Redshift, and I don't want to incur like additional dependencies, additional costs to upload a file. That's all I'm trying to do. So then let's go look at Daft. So to get started with Daft, we create a new Python environment and do pip install get Daft. It will pull in its dependencies for you. So to connect to S3 tables, we can use Daft's new catalog API, and this is something we just released. And we have a method where we import the catalog, and then we say catalog from ARN. And I give it the ARN of my table bucket, and that will give me back a Daft catalog object. And with this, I can start doing what I need to do. So I say my S3 table, call out get table, pass in my identifier, and now I have a DAF table. I call dot show, and this is what it prints back out. It's empty, but that schema looks correct. I have my X, my Y, my Z, my Boolean, my number, my string. So this looks good, but how did we get here? How are we able to read this? Going back, we have the S3 bucket with the Iceberg under the hood, and then we have the Daft engine. And the first thing I do is I go find that metadata.json. And when I get it, I pull that file, and then I use PyIceberg, static table. Given that JSON, I can go find all the objects. That was pretty easy. Happy about that. I still need to upload my Parquet file. So with our tables, you can write to them. Like I said, Daft has the ability to write Iceberg. So just like you do with an Iceberg append, I go to do my Daft table. I append my Parquet file. If you give it a string, it knows that that thing's a file, and it knows that it's Parquet because of that extension. But this throws an error. It was not going to be that easy. And the error that we have here, sorry guys in the back, is a not implemented error. And it's not that it's not coming from Daft though, which is interesting. It's coming from coming from PyIceberg. And if we look closer, it's coming from the no-op catalog, and it failed on commit table. These are some new concepts, so let's try to dissect this. To step back, how do you actually write data in Apache Iceberg? Well, the first thing you do is, again, you get that latest metadata file. You need to know where everything is. And then you actually perform the operation that you want to do to then insert, you need to put all those new files. It's S3. It's a pen don't, like you're just pushing stuff. So you put all those new files in there, and then you need to update and create the new metadata file. And then you need to tell everyone else that, okay, here's the new source of truth. This is where you find stuff. We put more stuff. This is the new metadata file. This whole thing we call a transaction. And the catalog is responsible for handling this transaction. But we just had a no-op catalog, and it can't do transactions. And so this is why we get the not implemented error. So we were never actually using an Iceberg catalog. We just pulled the metadata file and just read all the objects, but we don't have, Iceberg's catalog to handle this stuff for us. So how do we get one? Well, we could use the Iceberg REST catalog. This can handle the transaction for us. But like I was saying, S3 tables is not Iceberg REST, but we can make it work with Iceberg REST. In order to do that, we have to check a few boxes. The first one is we need to integrate with Analytics Services Preview. This one's in S3. When you create your table bucket, you'll see at the top of the screen, there's a huge banner that says Enable Integration. You need admin privileges, and you just click that box. Pretty good. And then you go over to Lake Formation, which is a new service, and you'll see this new section called Catalogs. And in there, you need to check some more boxes and create a glue catalog. And it's relatively easy. Honestly, like the biggest headache is permissions. So just doing everything with admin permissions, set up Lake Formation, enable glue, Iceberg REST. And this is the new state of things. So rather than Daft talking directly to S3 tables, it goes to Glue. And Glue has Iceberg REST, and Daft speaks Iceberg REST, and we should be able to do transactions now. So let's revisit this example, but instead of going just to this table bucket, let's go through to Iceberg REST. We'll go ahead, import the catalog from Daft again, but we're also going to import PyIceberg, the PyIceberg load catalog function. And it's kind of hard to see, but we're loading up an Iceberg REST catalog, and we give it the glue URL to say, go connect to this Iceberg catalog service. And then instead of saying, create a Daft catalog from an ARN, we're going to say, create a Daft catalog from the Iceberg catalog. And do a sanity check. We use this one and we call get table. We pass in our identifier and we get back our thing. And lo and behold, it is still empty. So this right here is I'm showing you that I got a little bit of data insert. I just used the daf like read parquet function. This will make a daf data frame, and dot show will just print it out. So we have 3 rows, and then I can call append, and it's okay this time. And then I do a points.show, and I see that my data's in there. I didn't have to call get table again. The Pi Iceberg handled the metadata refresh. It knew that I had written something. It knew that I had to go back through the catalog. It knew that I had to pick up the latest metadata file, and I got my data. But wait, there's more. So the catalog stuff is also integrated with our SQL API. So now when you have, say, like a SQL session, you can attach this S3 tables catalog to your SQL session and then just go ahead and write SQL. Select star from demo.points, show, that'll return a data frame, and you can see we can access all of this and write SQL statements over our S3 tables as well. And then here's what the whole thing looks like. And this has reads, writes, create namespaces, you name it. And all you got to do is, import a couple things, and it's like 4 functional lines of code. So looking forward, well, we're going to be releasing the support for S3 tables next week. But in the latest release that we just did this previous week or earlier this week, we introduced these catalogs, tables, and sessions. So you guys can already start working with them, and you can work with the Iceberg one. And yeah, we support writes today using the Iceberg REST catalog. You just can use the data frame write Iceberg. You pass in your Pi Iceberg table, and you can write stuff. And then we're on track to support Iceberg tables without AWS dependencies. So we have a path forward to be able to write using that, from table bucket ARN. You don't have to configure lake formation. You don't have to configure glue. We'll actually be able to write to these things directly to the table bucket. And then we'll be presenting in more detail at the Iceberg Summit on April 8th, where we'll get into more details of the code and have some more complex or more detailed examples. And then we have a little time at the end now. I think I'm right at 20. We're hiring, as Chan Chen shared. These are some of the roles. And if any of this interests you, please scan the QR code and feel free to email us. Yeah, I got a couple minutes for questions.
Hello. Hello. Cool. You, sir.
Thanks for a great talk. Can you actually go one slide back?
This one?
Yes. So supporting Iceberg without AWS dependencies. So I'm a little bit curious about that one, right? So what's going to be the catalog then, right?
Yes. So S3 tables is like a catalog service. It's just not an Iceberg catalog. So so we can't just use Pi Iceberg backed by S3 tables like API directly. We have to put that layer in between using Glue to make it speak the Iceberg REST protocol. So fortunately, S3 tables does have all the APIs to perform that transaction. It does have an API to put the latest metadata location. So what we'll do, and this is what I mean by we have a path forward, is we perform our updates, we push our files, we make our new metadata file, we put that in the bucket, and then we call the S3 tables update metadata location. And so now S3 tables is the catalog. Yeah. And that's what I mean by no dependencies. You don't have to go configure multiple services now. It'll just work.
You're going to still call their API.
Of course, of course. Correct. Oh yeah, I should have said about lake formation and
You said S3 table support fine-grained security. So, but how you support with S3 table row-based security and column-based security?
Yes. Yeah, no, that's a great question. That's what I worked on when I was at Amazon for 6 years before this, and I actually worked on row level and column level security with views. It's really interesting. I don't know about that. I only know about like namespace and table level security. You can do it at the catalog level because you have multiple, and you can do it with the like the key prefixes and stuff using like IAM traditional stuff. Late formation also has its own policy mechanism for access control, and that's on the like tables, namespaces, and catalogs. But when it comes to rows and it comes to columns, I think we'll have to wait and see what AWS possibly offers there.
Yeah, I think it would not be even possible because with S3 tables itself is just kind like a catalog, but the data is in regular bucket. In regular bucket is just a Parquet file, and there is no option to allow you to read part of Parquet file, but not the other part.
Yeah, exactly. We had to. There's more complex details on how we were actually able to accomplish row and column level security, but we had to do it by defining views, and you actually query those views. And so there is a layer of indirection over that. And like you were saying, well, if you just given them the bucket, then there's no indirection. So how are you going to keep the whatever rabbit in the hat?
One more. Where? Taylor?
Hi, yeah. So to my understanding, like you can technically write Iceberg tables on just general S3. Then S3 tables is like AWS's way to like optimize that and stuff. I never really looked into like if they made that information public, but I'm curious, like, is there any knowledge about how they've done that? And like in your experience, like how much of performance benefit does that make? Because I hear it's a heftier price tag.
Yeah, so it's $3 more per terabyte, which is honestly that's not too hefty. $3 per terabyte, but I don't know the details under the hood. Like I'm here. So I don't know the details under the hood, but I'm assuming if you know how the data is stored and you know what the workloads are, they're probably just choosing hardware and they're probably just optimizing that one path rather than just being like general object store. But
so question here, can somebody hear me? We can hear, right? So so one of the things is when you have these catalogs, you need to have them distributed across regions because the catalog is the ultimate truth that happens. And when you have a bidirectional updates happening, the replication that goes across becomes very cost prohibitive. What S3 tables are doing is they're doing one way in one region to go down to the S3. S3 is 7-way replicated. So they need an interface layer in between, which is the real ground truth, and then push to S3. So have you actually explored solutions where people for disaster recovery have the catalogs in 2 regions, and that's the ultimate truth that where happens? Just I want to check your brain. I'm fairly comfortable with Delta Lake and replications across regions. So we can take it offline if you don't have an answer. You don't need to answer now.
yeah, no, I don't have an answer. That's a good question. I didn't look into cross regions, just US West 2. So we're on PST. No, but that is a great question. We'll talk about it. That sounds interesting.
Okay. If you have more questions, come find Connor afterwards. We're gonna move on to the next one. On the topic of catalogs, now we have Arsham also presenting about catalogs. So let's give one more round of applause for Connor.
Hey. All right, let me see. Am I on time? Okay, we're good. Hey, everyone. Thanks for joining us today. The big thank you to Daft for hosting this. This is great. Happy to see more and more community events and kind of seeing more people involved in the Iceberg space. Great. So, Iceberg catalogs, great. Like Connor talked about it a bunch. This is fantastic. Like, I want to talk about catalogs because they are essentially the gateway to your data. We'll get into that a little bit, but I'm curious if anyone can count how many times I'm going to say catalog throughout this talk. It's going to be all about catalog, so just be ready. Yeah, so Yeah, I'm Arsham Islami. I'm a crazy founder. I'm visiting from Toronto. We're here for the Skydeck Accelerator. We have about 47 days left until our demo day, and we're going nuts. We're working on a SQL engine aggregator built on top of Iceberg. You bring your data to us. We give you the best query engine for your workloads. So yeah, again, why are catalogs so important? Why am I so passionate about catalogs? Why do I want to talk to you about catalogs today? I personally believe the file format wars are over. Seeing adoption from these industry giants like AWS, Snowflake, Databricks is a great sign. I think we can kind of move away from that and start to focus on what to do next with the data and get actionable insights. But there's one more nemesis kind of in my thing. I'd love to know what you guys think about data catalogs. You know, what is a data catalog? Does anyone have an answer? Catalog for data, cool. It's such an ambiguous term. Whenever I see this term online, I get such a crazy itch. Is it your schema registry? Is it your metadata store? Is it for your business context, for discovery? It's nuts. We got to work on something better. Throughout this talk, I'm mainly going to talk about Iceberg catalogs, the technical catalog, and whatnot. Okay, so yeah, why shouldn't you listen to me? Like I said earlier, I'm just some crazy founder. Yeah, there's tons of them out there, so be aware of that. If you are not interested in the Iceberg ecosystem, there's probably no point in kind of listening to me today. If you love your current catalog and you're not looking for new tools or new technologies, no point in listening. Okay, so how did we get here? I want to walk through a little bit of the history of like the big data space, kind of like a little bit of what happened and kind of why we ended up here. Where does the catalog fit in and all that? Cool. Okay, so anyone seen this graph before and can maybe guess the axes? I'll start you off with the x-axis. It is actually years. What do you guys think is the y-axis that kind of tops out at 2 billion in 2010? You got a shy crowd. What was that? Phones. Oh, pretty close. This is actually, was there one more? Internet. Okay, very good. This is the number of active internet users over time. This is kind of what sparked the big data space. Companies started to deal with web scale data. As users start to grow from like the 2000 era to when we started to get phones and social media started to produce like user generated content, the amount of internet users spiked and also the amount of data that we were generating every day spiked massively. This is a 4x growth in just the users. What did this kind of cause? Before the 2000 era, we were all dealing with these kind of vertically scalable solutions like Oracle, MySQL. Your compute and storage was coupled together. If you wanted more performance out of your SQL engine, your query engine, because your data is growing, your only option was really to upsize your data set or your compute cluster and whatever. Back then, there wasn't really an idea of like compute clusters. Really, there was some sharding things that you could do and whatnot. But Teradata and these massively parallel processing systems came out, like Teradata, Netezza, Greenplum, and they were all about distributing the data to a bunch of different workers. They're all proprietary solutions, and they're very expensive. And then something really cool happened. It came out of Google. It was kind of like the secret sauce to their solution. Anyone know what that is at the very end on the right? Average, okay, kind of. This is kind of like an algorithm. MapReduce, who said it? Good, very good. MapReduce, great. So what MapReduce did is it allowed Google to kind of distribute their data across multiple different drives and hardware components, and then have MapReduce go and kind of shuffle the data and organize it in a way to kind of do more efficient operations on large scale data sets. These systems kind of worked at the time. This is kind of early 2000s still, but it was really complex. It was usually internally built by these bigger companies, and it wasn't really available. Then we kind of entered the Hadoop era. This was it was like, think of like mid 2006 to 2015, 2016. There's still tons of companies using Hadoop. But what did Hadoop do? It took like three core technologies of this kind of MapReduce space of the distributed storage, which is the Hadoop distributed file storage layer. MapReduce, they kind of reverse engineered the MapReduce algorithm. And then they had a resource orchestrator that would co-manage these kind of compute nodes and storage nodes and whatnot, and kind of manage the life cycle of everything you need to do to get data out of this data ecosystem. Yeah, it was huge. Awesome. Democratized it for everyone that wanted to do big data workloads, but there was no real way to write SQL. You couldn't really give MapReduce to your analyst, your business content analyst that knew SQL and say, oh, pull the data, generate your reports. It wasn't really possible until Hive a couple of years later. This was the first kind of like SQL engine on Hadoop, which kind of changed the game. Analysts now had access to tons and tons and tons of data. It did have some limitations though. It's, you know, when you're doing things through Hive, it's really just read-only. It's all read-only. It's only views and really high latency. So if you messed up your report, you're gonna have to wait a ton of time to kind of get the next one. In the early 2010s, we started to see some optimizations as more and more companies got involved in the space. We started to see the Avro file format. We started to see Parquet. Avro did, you know, schema evolution a lot better. You didn't have to break your whole Hadoop setup. We needed schema migrations. And then Parquet did a better job for columnar lookup. So think of Avro as like the write engine. It was like, or the write format you want to use. It's really row-based, better serialization, better compression, really good for like write-heavy workloads. And then Parquet is for like the reads. Okay, there we go. So we are kind of entering the Lakehouse era. Depending on who you talk to, we're already there. But you know, what is a lakehouse? A lakehouse combines kind of the best of a data warehouse and a data lake. All your data lives in object store, which is nice and cheap. You have your data stored in open table formats like Iceberg and Delta and Hootie. And then because of this open table format and because your data is actually on object storage, you can use whatever query engine you want now. You can figure out what query engine is best for your workload and apply that as you need. So kind of why are companies adopting lakehouses? Obviously, everyone knows we're all in data here. Data gives a business the edge on their competition. Whoever has the most data can build a moat and all that. Lakehouses made it cheaper, so now you could do things with more and more data. It's more performant than a typical lakehouse or as a data lake. And there's less vendor lock-in. A lot of these components are open source and able for you to move things around. Even for your object store, you can use things like MinIO, which is open source. All right. Oh, so this is a big one. So why do we need a catalog? We got our data, we got our query engines, we got our file formats. What really is the point of a catalog? You know, I've heard this analogy where, you know, your catalog, your data catalog, your Iceberg catalog is really like your taxi driver when you land from the airport, but it kind of tells you where to go, which is, you know, where you go is where your data lives and whatnot, but it doesn't really sit with me too well. I like to think of a data catalog as kind of like an airport. And I think of like the cargo as the data that gets moved around by planes, which are your query engines. The airport is the thing that facilitates, you know, where the people need to go, who should get on one plane, doing the security to make sure that the wrong people don't, you know, get involved and whatnot, or people don't get the wrong things. So what do catalogs do? They manage your files. They make sure they know like, you know, what's where and whatnot. They help you do some transaction management. And finally, they do some things for query optimization as well. Nowadays, with newer catalogs, we see lots and lots of new superpowers that they give to your query engines and whatnot when it comes to partitioning, compaction, and whatever. But it's an evolving space. Just the other day, we saw new new tools and whatnot. DAF's coming out with cool stuff already. Like, this is already an outdated presentation. Great. Okay, so what are the different types of catalogs right now? There's service-based catalogs. These essentially store the metadata in a relational database. There's like a service that's constantly running, keeping track of things, and this is a centralized approach. Whenever you want to go access your data, you have to go to this service, ask it for different things through an API, and you get your data as you need. So Hive metadata store was kind of one of the first ones. By default, it runs in service mode, but it can run in different ways. But as soon as we saw this come up, multiple different companies saw like a scaling issue with the Hive metadata store. They started making their own private forks, and it kind of pulled away from like the open source like thesis that like Hive was built upon. Yeah, so it kind of takes us to the next type of catalog, which is file-based catalogs. This is a really cool concept. So in this case, instead of storing the data in a relational, database service, the metadata actually is stored alongside the data itself. So no longer do you need like this like uptime that needs to be, you got to have your SRE team manage and make sure that it doesn't go down or whatever. It's just in with your data. As long as your object store is up, you can query the data now. There are some challenges here because the different query engines are now responsible for kind of managing the data, but the advantage is you get this decentralized approach. It's very simple. Like I said, there's no real like external database dependencies or services you need to worry about. It's super resilient, which is really nice. One of the hard parts about this though is if you want to go in and do like a manual update or edit or whatever, you are now at the mercy of all these files that you've generated, and it's really difficult. Tuning this kind of system for performance is also challenging as well. You're kind of having to do a lot of analysis manually, which is tough. Brings us to today. REST catalogs are, I believe, the future on Iceberg. REST catalogs kind of give us the best of these two worlds. The metadata is still stored in files inside object store, but there's now a service that kind of sits on in front of it and centralizes things via an API. Why this is cool is like you can have really high concurrency with this solution, and the REST Iceberg spec is actually open sourced. That means that if there's something you don't want, like you can go and change this. You can go take one of the open source catalogs and do it your way. Cool. I'm going to walk through a couple of the popular original catalogs that have been around, and we'll talk about kind of the strengths that they have and whatnot. Okay, first, Tabular. Tabular was one of the first catalogs around, built by the creators of Iceberg, and it strictly follows the REST spec. I want to think of some analogies for kind of these different catalogs to kind of represent them in a more like human-friendly way. And I thought about screwdrivers. So we can think of Tabular as like your most typical classic screwdriver. Just a typical, flathead screwdriver, nothing fancy, no bells and whistles. By the way, I generated this with AI, and it was really challenging. AI does not know how to generate screwdrivers. You'll see it in the next one. This is actually one of the better looking ones that actually kind of looks like a screwdriver. Next is Glue. Glue was actually one of the earlier implementations of REST as well, built on top of Glue's like initial work on the metadata store that they have. Glue's biggest advantage, I feel like, is that you get like really easy integration with all the other services that AWS gives you. There's just so many tools available to you. It's unbelievable. Glue does so many things other than just being a data catalog. You can do things like automated ETL jobs. You can build crawlers out of it. You can do like elastic views, ML stuff. It's just unbelievable how many features they have under Glue. Actively, it's being improved. Like we saw Connor talk about how like Glue is now building in things with like the S3 table features and whatnot, and you got the weight of Amazon behind it, so you know it's going to be good. Yeah, Glue to me is one of these guys, a multi-purpose tool. It's a screwdriver as well, but you can do so many things with it. Yeah. Okay, so we got Nessie. So Nessie was one of the first-ish open source versions of an Iceberg REST catalog. One of the coolest thing about Nessie was how it has like this Git-like branching for your data. It gives you kind of like first, I guess the best way to say it is like you can change your data via like snapshots really easily in like a Git-like format. So easy to tag things. If you want like a developer branch of your data set, you can easily do it. Really nice. It's built by the early innovators in the space of Dremio. They've been working on this for a while, and we're gonna see this slowly get rolled into Polaris, built by Iceberg. Anyway, so Nessie, it's gonna be your quick exchange screwdriver. This is what I meant by it not being very good. The tips of screwdrivers is a terrible job. I don't know why I think screwdrivers are like this, but think of it as Nessie as like a quick change tool. You can quickly change the different versions of your data really fast. All right, let's talk about some of the new kids. I'm running a bit out of time. It seems like the trend with the new tools and the space, the catalog space is really open source is kind of firsthand. We see tools like Polaris being built by contributions from Snowflake. They're doing a really good job. I think they're aiming to get their V1 done by Q2 of this year. It seems like from what I've been reading, their security model is like a first-class citizen. They're doing lots of stuff on RBAC, fine-grained access control and whatnot. One of my favorite features, though, is that the nested namespaces. Having the ability to do nested namespaces is really cool. Not a big fan of the previous approaches. Yeah, this is your really high scale, really fancy screwdriver. It's got a little blocking mechanism. You feel like a king using this. All right, next I got Gravitino. This is Apache open source as well. They have a really unique approach to catalogs. It's not your typical just, rest and go get it done. They're kind of thinking of things as like a broader scope. They want their catalog to be accessing lots of different things, not just Iceberg tables. This is like a catalog that can read from other catalogs, bring in table sources from everywhere. And also they're doing some things with the geo-distribution. I know you guys were interested in this. Like it seems like this is a core concept for them that they want to tackle. So really cool. I think of them as like a socket set. You can fit whatever bit you want into them. Yeah. And finally, and there's lots of different, there's lots of different Iceberg catalogs, but I'm only highlighting a few. These are the ones that are fairly far along. I want to highlight Lakekeeper. I think the biggest thing with Lakekeeper is that it's super fast. Very light. It's not a big install. It's very easy to install, very fast, and it's Kubernetes native. So if you're deploying this yourself, they give you Helm files. They do all the things you need to kind of get it done. And they do have one interesting feature I actually want to bring up is they kind of have data contracts built in to the catalog. So you can define data contract right in the catalog itself. And if someone pushes something that's out of scope or the schema's change or whatever, it'll actually reject that change for you without you having to, go around in loops and figure out what happened. Yeah, they're going to be the fastest way for you to, screw things in. Okay, cool. So I'm just about done for time. I want to talk a little bit about kind of where I want things to head, just given my nemesis of data catalogs and Iceberg catalog, all this kind of stuff. We are slowly seeing this proliferation of like all these tools kind of coming together and consolidating on their feature sets and whatnot. This really gets me excited. I would love to have one tool where I can do all my governance. I can put my contracts there. I can access all my data from there. Even if it's from other catalogs that some specific team uses. Data Hub, which is like one of the business-driven catalogs, just like last week released their Iceberg spec as well. So we're seeing people do their business context in the same place where they're pulling their data as well. This is fantastic. More of this, please. Make me really happy. Yeah, that's about it. Thanks, everyone. Happy to answer any questions.
Cool. Thank you, Arsham. My first question is, how many times was the word catalogs said?
Oh,
Too many?
yeah, too many, too many.
Okay, we'll take like 2 or 3. So I'll go in the back and then.
Hey, thank you. That was really nice, very insightful. Can there be multiple catalogs pointing at your storage at the same time?
I think it depends. If you're using like a file-based catalog, you might end up getting some writes at the same time as the other one's writing, and you'll have some conflicts. I think it's recommended to have one catalog. If you're interested in having multiple different catalogs spread out throughout your use case for different workflows, I would highly recommend looking at Gravitino and how they do reading from other catalogs. So you can have one main catalog and then have multiple smaller catalogs on different subsets.
Gotcha. Thank you. Thanks a lot.
So I want to ask you why Nest namespace is your favorite feature of the Polaris, and can you share any use case for that?
Yeah. So at Graybeam, what we do is we help people run their Snowflake workloads on other query engines, and part of that step is actually to move some of this data out into Iceberg. And I want to create an equivalent environment in Iceberg to Snowflake. Can't really do that with all the current like I couldn't do it on Glue. That was a big pain point. And I'm like, now I have to nest the schema name in the table name and put some fancy delimiter in there. Just let me do normal namespaces.
Cool. Do we have one more? Nope. Yes? Well, okay.
How have you thought about migrating people off of Hive onto one of the more modern catalogs?
Well, Hive to so okay. I think it depends what your data is stored at. If it's stored as like Parquet, it's actually fairly, depending on your data volume size, to rewrite that as Iceberg and then plug in a different catalog right then and there. That's actually pretty doable. It's actually pretty built out. There's people doing it right now at scale. But if you have like sequence files, like Hadoop native files, it might be a little bit more challenging to get those out into like Avro or Parquet and then do the translation. But I think you need to start at the data level, move those over to something that's easier to integrate into Iceberg, and then go from there.
Thank you.
So we're gonna go into a 5-minute break right now. If you have more questions, I say go grab him right now. Grab pizza, grab a drink. I'll throw the Luma QR code back onto the screen, and then I will see you guys in 5 minutes. Thank you. Hello. Hi, everybody. If you can hear me, it's time to sit back down. It's actually been an 8-minute break. So if you can hear me, please sit down.
I'm gonna listen.
No, it's okay. Oh, that's yeah, I could never do that.
It's not a talent. It's something you can.
Oh, really?
You curl your tongue and then leave a little bit of air.
I saw our shop. It's like
Yeah, we can look at this.
so the sense of so maybe you try. I saw.
Yeah, this is some slide, right?
Yeah.
I know it's not gonna show you slides because.
Oh, it shouldn't.
Yeah.
Okay, clicker. If it doesn't work, okay, everybody, if you're still standing, please sit back down. I will come yell at you. Hello, everybody. Please come sit down. Sit down. Okay. Okay, what's up? Okay, are we good? All right. So we have two more for the night. We have Emery giving a talk about security of Iceberg. And then not last but not least, we have Anirudh talking about Iceberg deletion vectors, which I have no idea what that's about. So I'm excited for that one. But I saw on a LinkedIn comment that Emery is the security guy. So very excited for this one. And here you go.
Hello. All right, you can hear me. Cool. Anybody on security here? Oh man, I called you before. Okay, I'm the least data person that's going to talk today. And if you have data questions, I try to answer, but it might be wrong. So, a little bit about me before me. That's a free book right there for Apache Iceberg, the definitive guide. If you want to take a picture of it and then use the QR code, I'm going to leave it there for a while. It's written by my boss, top boss, I guess, the co-founder Tomer and Alex Merced. If you worked on Iceberg, you probably read one article at least from him. And he's the guy actually who pushed me into this. This is awesome. Some more. What kind of QR code reader you're using? It took forever. Just kidding. All right. Also, another one, good blog where I don't write there. I think Alex write way more than I do. Again, like I said, I'm the least data guy here. But then who am I? The name is Emre. I've been in security too long, over 25 years, and I'm the Chief Information Security Officer for Dremio, and a bunch of titles there, but the end is like I'm the security guy, right? So that's kind of I want to talk about a little bit like the security side of the world because believe it or not, all the hackers are not after systems; they're after your data, the data that you guys are managing. They couldn't care less about the systems. Well, unless they're mining Bitcoin and stuff, but that's a different thing. You know that, right? Okay, cool. I want to talk a little bit about layers of access, what that means from a security perspective. Not like from a data perspective, you know this way better than I do, but from a security perspective, let's a little bit talk about like which layers do we have in the security, like when I design a security system, which layers I look at it and which layers I want to protect and kind of like you should protect. I'm using all AWS stuff here, but this is, you can take this out, you can put Azure, you can take this out, you can put GCP, whatever, it's pretty much the same. I just had to choose one, I chose AWS. This is a typical, like, from a security point of view, typical thing, right? Like, hey, Emre, here's the thing. Go protect this, right? This is what I see. For me, the data is stored in an S3 bucket. Could have been stored in anywhere, Minio, whatever, doesn't matter, right? And there's a VPC there, some engine that is going to read that, some ETL operations that's going to read that, some data, right? There are the other data sources, and then there's a Lambda function that does some magic that somebody wrote in 2017, and you have no idea what it does, but it's there, right? So that's one of those, and then that's kind of the layers that the storage layer, and then the engine layer, and then the account itself. And then you have many of those, right? Like you have the finance guys who have an AWS account, you have a, whatever, right? So that's kind of what it is. And I put some cute narwhals because that's our logo. I had to represent, right? So let's start with the file bucket layer, right? Like what can we do there? And think about, like, let's play a little bit of adversary in here. What's the adversary, like who's your threat model? What's your threat model? What's your appetite for risk? Do you consider AWS as a threat? Do you trust them fully? Right? Like, is this a good starting point for you, or is it not? Right? Think about it that way. Does AWS take all your data that you store here and do something with it? Or somebody who lives in AWS that don't know about can actually get that data from there? Because that's where it all starts. That's where everything is stored, right? So depending on what your risk appetite is, what can you do about it, right? Like you can encrypt data at rest, right? And that kind of prevents someone walking into a hard drive, taking it out of there, going out, and then sell it on eBay, and then somebody finds your data right away. That's kind of what it is, mainly, when you're encrypted at rest. But so that's what you're preventing, actually, right? Or you're really not preventing AWS reading that data, because guess what? AWS is encrypting that data. So now that's your trust base. If you don't trust AWS, if you don't trust their encryption, you don't trust their encryption, you don't trust their key, you don't trust it, that's trust has to start somewhere, right? But the good thing is you have options. You can do KMS, which is customer managed keys for S3. Well, that means, hey, here's my key, just use it to encrypt it. But then again, you're giving the adversary again. Like if you think AWS is your threat, which I don't, but then that's also goes away. You cannot do KMS anymore. Well, there's I didn't put it in there, but you can actually store, encrypt it, and then store it, right? Then you can encrypt it offline, hopefully not in an EC2 bucket. If you don't trust the AWS, that's gone too, right? Then again, like what I'm trying to tell you here is like you have options depending on your risk appetite. You trust AWS, you trust their key, go ahead and encrypt it. Somebody's going to walk out with the hard drive and they won't have a decrypted data. They don't have clear text, so that's great, right? But if you don't trust AWS, then there are options. You can actually encrypt it offline and then store it in there. But how are you going to read it? That's a different story, right? Again, restrict access to S3 buckets using IAM policies. That's kind of big, and that's where a lot of leaks happen. And I'm going to talk about a little bit leaks, what happened before, which will happen again. Job security, And then if you're not comfortable with IAM policies, go ahead and read them, and that gives you a lot of control over your reading, writing, who can read it, which role can read it, which role can write it, which role can delete it, right? This type of access, and which role can read the bucket, the entire thing, how you design them, and be comfortable with them. And then, but however, that's not like, but wait, there's more, right? There's always that. You can use control. You can actually control network access to your S3 buckets by using VPC endpoints. What does that mean? Anybody know what VPC endpoint is? So yeah, and VPC endpoint is basically that cute logo right there. This is depending on your policy, of course. You can actually tie the S3 bucket to a VPC, right, or a something, whatever that principle is. So which means even if you screw up the bucket policy, it's not going to be open to the world. And us security people love to design things like an onion, right? Like one security control on top of another security control. So think about it that way. Like you have the IAM policy, maybe we should put a VPC endpoint because only this VPC is going to read this bucket, right? Like, and it's pretty easy to get lost after that, but still, it's good. Some logging and monitoring is, I think, essentials. If not for security, it's good for cost, right? So, and then some S3 object log to prevent accidental malicious deletion of existing objects. Right? So that also, I find it like, it saved, like once you see logs, oh, it's object log. I can't delete it. Well, maybe there's some bad guy is trying to delete it, but they don't know that you have an object log there. It's a good detection engine there. Signal. All right, so let's talk a little bit about S3 data leaks. It happened before, it's going to happen again. It's going to happen less, but it's still going to happen. So in 2017, Verizon data leak exposed 6 million users' data because of the misconfigured S3 bucket. And then it happens, but if they had maybe a VPC endpoint, right? Maybe they were just accessing from that VPC, they still wouldn't have that expose it, even if they opened it to the world in the bucket policy, right? So it's a different layer that was protecting it. 2017, Time Warner I'm not here to shame companies, just examples. Time Warner exposed in these links, they go to their explanation, not some media article. I hate that. Time Warner exposed 600 gigabytes of customer data, including email addresses and account information. Yeah, 600 gigabyte is big especially for 2017, right? Capital One data breach was an interesting one. They exposed 106 million customers. Some interesting data there. Go ahead and search for it. And if you're a Capital One customer, you go ahead and search for it. Okay, especially. There was a misconfigured firewall which exposed the S3 bucket. I don't know how you protect S3 bucket with a firewall. That's bullshit, in my opinion. That's explanation. Sorry, but like maybe they were trying to say VPC endpoint was configured wrong or something like that. But there's no firewall that protects S3 bucket. Period. So, 2020 Twilio exposed 885 gigabyte. It's kind of growing, right? The size of things, phone numbers, message transcripts. This is the interesting one. Does anybody know this incident at all, or have you ever heard of it, the Twilio one? They were serving a JavaScript file from that bucket that was compromised, and the attacker actually modified the JavaScript so that now the JavaScript was pulled by every Twilio client out there, which was awesome, isn't it? That's where I would put my exploit. So, because you trust that JavaScript is served by Twilio, but the S3 bucket that is serving it is compromised. So what do you do now? Think about it. Yeah. So these are some real world examples. I just, I didn't have a hard time to find for. Let me put it this way. There's a ton of them. There's Pegasus Airlines that lost, I think, millions of data, et cetera, et cetera. There's a lot of them. From S3, just S3. Remember, we're on just base layer now. Now let's talk about more. Well, what about the infrastructure? Right? What's the let's talk about a little bit like the top part of it. This is a lot of data leaks happen here too. What do we have here? Like dragons live here, right? What is it? There's a network there. Okay. Nobody knows how network works, right? So network, the packets go, come back, and I don't know how it works. I do. I spend half of my life as a network engineer, but still, there's a lot of empty knowledge there, which is thanks to cloud infrastructure. It's super easy. Everybody's a network guru now because you can click a button and then create a VPC and then a network and a gateway and But actually, what's going on under? Again, depends on your risk appetite. Do you trust the network that AWS provides you? Right? Like again, where does your trust start? And then you go after. Like I trust it, but do you trust the other workload that is running next to you? Whose workload is that? Can they tap into network? Can they see my traffic? Can they? Did somebody enable the, I don't know, the network like packet collection somewhere? An admin did that, etc. There's a lot of like threats there, and also like there's a bunch of traditional compute stuff there, right? Like, are they open to the internet? Is it running a Hadoop that is like, I don't know, 5 years old? I'm not looking at you. Yeah, right. So, and then do we have a like did somebody did support people install the Hadoop instance that matched the customer's Hadoop instance, and then they left it at the default passwords, and now what? Like they're on the internet. I'll give you 5 minutes for them to find it. Takes literally 5 minutes. Out of all these internet, the moment you open a port, it takes 5 minutes for them to come. Just let you know. Okay. BI tools are there, connectors, Lambda functions. Is your Lambda function like secure? Is it, again, like what's your adversary? Is it writing something on, because Lambda, up until like recently, it was running on AWS side of the world, right? Over the fence. So when you do that, and if you have like, I don't know, your private key, and you give it to Lambda function that actually would actually traverse your organization or your AWS account that it was running on AWS premises, what if it crashes? Does it take a crash dump? Is your private key there now forever? Who cleans up after that? Et cetera, et cetera, et cetera. Can somebody make it crash and then some malicious guy can actually crash a Lambda function and then read that? Or like, there's a bunch of different interesting challenges there. And yeah, and they're all security controls, but that will take another 2-3 like sessions of me talking here, but just a couple of examples. There are other data sources that might not be yours, right? Like, and then you have some sort of like thing in mind, and it's great, and it's working, and it's compromised. Now, not only they have access to yours, and then maybe there's a path here to this finance database, whatever that is, right? You don't even know, or you don't. Depends, right? So again, like that's not yours. Some random guy spun up something, and then that got compromised. And then if you don't have like security walls around it, like security groups and stuff, now you're compromised because again, like it will take them one port scan to find what is out there, and then they're gonna start trying. Hopefully, you have some sort of detections in between, like oh my God, it's compromised. We got to do some action. Let's shut it down, etc., etc. Or you can jail your workloads. These are the bored people. They don't like security, so they're leaving. Just kidding, just kidding. Like, can you do like isolation through VPC? Can you do isolation through AWS account? Can you do isolation via security groups, etc., etc.? So here are some tools for this. See, I learned how to click now. Click here. Yeah, it's working now. Great. Segmentation. I love segmentation because segmentation is like super straight boundary. Like thou shall not pass. Right. That's the moment where Gandalf was like, okay, I'm a Lord of the Rings geek. All right, I'll just shut up. Groups, security groups. I think, especially if you have a Terraform environment, please. I mean, this is perfect. Like you just define once and you're done. You're never ever gonna touch it again. It's not like you spin up an instance of what was my security group. It's not that. Like if you're Terraform, perfect isolation right there with security groups. I mean, again, this is AWS, but Azure or whatever, GCP, Oracle Cloud, I have no idea how it works. But yeah, I mean, those all have their counterparts, right? Workload isolation, data source isolation, access to the data source isolation, like this workload can do this one with this type of access, and that one can come to the same one with a different level of access. It gets complicated, but that's again, what's your adversary, right? Like what's your threat level? What's your risk level that you can accept in there? AWS account level isolation. Some of my customers are like, no. You have your own AWS account. You're going to connect to my data sources from there. I don't want you to near any of my. Some of them are like, yeah, sure, right next to the data source, depending on their risk appetite, your risk appetite. Again, external party security is an interesting one. Like, you have a ton of interaction with GitHub. What do you put there? Do you put AWS keys? Do you put access keys? Do you put tokens, personal access tokens? Once you put it in there, then all of a sudden, like it's in a different threat level. If the repo is public, it's public. Oh my God, right? It's gone. And then if you change it, it's in the commit. Can you go, how many commits can you go back and then like do it? Like find it over there. Trufflehog finds it like this, right? So it's a tool to find the credentials committed in the GitHub. Yeah, so let's talk about real life stuff. Cloud infrastructure breaches. Now it's a different type of breach. 2022 or 2024, we don't know very well. Toyota didn't do a good job. You can click on it. There was a cloud misconfiguration, whatever that was. And then we don't know, of course. And then that exposed the backup server. And then they got into the backup server. What does backup do? It backs up data. Now you don't need access to S3 bucket because it's there. Every version is there. So if I'm a hacker, okay, let's say I'm not a hacker, but I'm a bad guy, I would plunder your backup servers like this because there's every type of version in there. That's where I would go, right? 2022, this is an interesting one, Cosmos DB vulnerability. This was Jupyter Notebook related vulnerability. And this was giving unauthorized data access to certain like Jupyter instances and from Jupyter instances to backend Cosmos DB, which was a bug, and they had to patch it. I'm sure their security operations center was burning that day. 2019, this I love this one. Imperva. Do you know what Imperva does? It's a security tool. They do web application firewall. What they did is that one of their AWS compute instance was compromised. Remember if you go back to one of these were compromised, or these, right? And then what happened? They got an AWS key inside the server because that's where you commit your that's why they have to access, right? That's how you access most of the tools. And then they got the key from there, and they went and plundered their backend database from using that access key. So again, this is why I'm telling you all of this is because this is another layer that you have to think about when securing a workload or an infrastructure, a data infrastructure, or any infrastructure. It doesn't matter. That's why I'm not a data guy. I'm a security guy. Like I have to today secure a data infrastructure. Tomorrow I get a secure, I don't know, web application, right? So that's kind of how I look into these things. Let's talk a little bit about catalog layer, which is the weakest part of me, I must admit. And that guy knows way more Helloc than I do. So the trend is, at least we're trying to push the trend to control in one place all these access to all these different places that you have in an Iceberg catalog. What's the good thing about it? Well, it's centralized. There's one place where you're gonna define this, and then you have different sources, and then that's where the catalog is gonna give you that whatever you want to do, right? And then namespace organization, right? They have the logical grouping of these, and then now you can logically give access to a group, something, right? Like maybe Counter's access versus Emirates access to some logical groups are different, but they still have that logical group, right? Back. I love that word because that's the hardest part of any solution, in my opinion. Authorization is the hardest one. Authentication, solved problem. Authorization, we're still happening, right? And then yeah, you can define roles, you can define permissions, you can define users, of course, and then who has that role that has that permission, right? That's that cascading thing, and then you can do advanced catalog support cell level access, right? Like what do you? I had to deal with this like totally different data, like at Salesforce, for example. I had to deal with like a bunch of cell level access to things, like, but it's not evident in the. And once the data is very clearly defined what it is, it's easy. When it's not that easy, right? This one is an interesting one because I want to talk to. This is the most iceberg thing I'm going to talk today, right? So I want a little bit talk about what credential vending is, which is an interesting concept for me, and I've been working with Nessie guys a ton and Polaris guys a ton on this. This is based in the middle. You have a run-of-the-mill Iceberg client, whatever you want to do it, right? And of course, you should support credential vending. And then we have a REST catalog, which could be Nessie, Polaris. For now, like I choose those two because I'm kind of always working with them. I'm biased. Everybody is. S3 bucket or GCS, wherever you store your data. ADLS is harder from this perspective, from an STS perspective. There's not like a super clear cut for this, but those two work really good with this model. So in this example, you're gonna select something from the table, right? This is by the extent of MySQL, right? So I know there's a star here, somewhere here, but I didn't put it. So, and then this one is the catalog actually looks from the table name or your namespace name, like where like do you have access to this? Because that's what you defined in the catalog, right? That we were talking about one slide before, right? And then okay, it's like, and then the catalog reaches out to S3 bucket because they have some sort of like trust relationship between them, like via access key or some sort of role ownership. And then they generate a temporary credential for that IAM policy, right? For this person. Now, this could be a couple of things. It could be a signed URL. And are you familiar with signed URL, everybody? And then, or it could be a temporary token, right? It could be one type of token that is defined. Then the Iceberg client from that point on, right? And then they basically go ahead and use that token. Why do we put this now in the middle? Well, this is where, first of all, you enforce the access, right? And then the other thing is that the other important thing is that these credentials are short-lived. Well, short is an interesting thing. 5 seconds is a short thing. Sometimes 5 days is a short-lived credential, but it's way shorter than like forever credential, right? And then the catalogs knows how to rotate the credential that they handed to the client. They also know how to rotate the credentials that they have to generate those signed URLs and everything. So which gives you 2 levels of like security level that I like as a security person. You might like or you might not like, because if you're managing client tokens, that's not fun, right? But as a security person, I like it because I don't have a forever token, right? I like this is like, let's say 5 days, and let's say this one is 5 hours. Now you have an exposure date of five days max, right? And that 5 days max is actually the worst credential, because that's the credential that allows you to create many credentials, which is that's the credential of credentials, which is I'm kind of like scared of it. So that's the part, like depending on your appetite, you can do, I don't know, 3 hours of main credential that constantly repeat changing it, and then like 5 seconds of it. Depends on how much data access do you need, how fast do you need, et cetera, right? So that's, again, depending. A lot of security stuff is depending on your risk appetite, right? The important thing is that having the tools. What else do I have? I have this step-by-step. I kind of went through it, but I'm not going to go do it again. But are you guys going to publish the slides, or then you have it. There you go. Some links. I don't know what they are. Intro to Iceberg. Let me read it for you. For the guys at the back. Postgres to dashboard. I don't know what it is. SQL Server dashboard. MongoDB dashboard. I don't know. So, but they are good things. Alex gave them to me. They are good. I trust Alex. There's a podcast also. That's the Database podcast that we have. I think Tomer runs this. Tomer is a cool guy. Go ahead and listen to him. He has some really good guests. I was listening, although I'm not a data guy. I was listening in. Yeah. Well, that's pretty much it. Any questions?
Any questions? We'll take like 1 or 2.
So data catalog, I suppose it's a single point of failure now, and do you need to protect it even more? And can you sleep at night?
Yes, that's an excellent question. Security control is always a single point of failure. Always. I mean, there are rare occasions that you don't have that, but that's when you design it layer by layer, right? So like from a security control perspective, yes, definitely. This is where you like, is Okta your single sign-on? Is it single sign-on? Is a single point of failure? Yes, right? So, but also like, which one is worse? Like managing in one place and rotating in one place and giving access in one place versus like 6 different places. And then well, I mean, I can go either way. I can explain the benefits of either way. Like if you have 6, if you lose one credential, you only 1/6 of your environment is exposed, right? But if you do it in one place, everything's exposed. So there's that. If you look at from that point of view, yeah, having 6 of them is better. But then how are you going to do credential management? How are you going to do rotation? How are you going to, et cetera, et cetera? Yeah, the question is if we are enforcing this on the catalog level, what the client needs to do, right? Iceberg client. Iceberg client needs to support, first of all, vending credentials. And I think I cannot name them, but I have it in my notes. But yeah, that's one thing that definitely needs to happen. And then I'm hoping that the standard is actually enforcing this. And then the other thing that I'm hoping is that how to, if your client token expired on the client, and then you actually re-request the client. So it's there's some sort of a retransmit logic that you have to do, unless it's a one-time thing, right? If it's a one-time thing, there's no problem. Yeah, that's kind of new, I think. Yeah, and then that's the Nessie is supporting that, Plur is supporting that, as far as I know. I'm biased, super biased on that, and then that's what it is. I think the other thing that I can tell you is from a like the Iceberg V 1.8 version 1.8 now has support for refresh credentials, right? From an OAuth perspective, though, not from vending credentials perspective, right? So I think since now once you know how to refresh credentials, the next thing is like it shouldn't be a problem to refresh vending credentials, right? So yeah.
Yeah, one more question. No? So can I just slap a 2-factor on? I'm just kidding.
No.
That's a joke.
No.
Just kidding.
If you use passkey, maybe.
Okay. If no more questions.
Anything else?
Anything else? Okay, let's give a round of applause. And then last but not least, we have Anirudh from Databricks. Perfect.
Thank you, Chan Chan. Shout out to DAF for hosting this great event. Shout out to all of our various sponsors. Super excited to talk about Iceberg v3's deletion vectors, aka row-level deletes. My name is Anirudh. I'm currently a product manager at Databricks, and we're going to start with the history of row-level deletes back in Hive, before Iceberg, give some context on what we're trying to accomplish here, and then work our way forwards through each iteration of Iceberg to where we're going to go in the future with the deletion vectors. When I first started learning about this topic, it was really weird. If I told you that you couldn't delete something, it feels very awkward. It feels almost like you don't believe me when I say that. If you open up any Excel file, a Google Sheets spreadsheet, you can delete any row, any column. No one ever asks you any questions about what's happening. So I wanted to actually start, before we even Hive, why exactly would we even consider spending any time about row-level deletes? And the answer has to do with how large-scale data storage works. These things called data lakes. Data lakes need high scalability and high throughput. So they're typically built on object storage as opposed to a typical file system that we might use. A good way to think about it is you have a bunch of buckets. And you can arbitrarily add and remove buckets as you need to. Your files can be located wherever that you want on the buckets, and that allows you to build these really, really high scale systems. The context, though, is that if you want to get any individual file, you have to go via some API proxy that will decode what bucket you need to actually access. So an example here is I have some Iceberg file that's located in bucket number 5. So I go to the API proxy, and that tells me exactly where I need to go. The API, though, is somewhat limited. As a result of this lack of hierarchy that allows us to scale somewhat arbitrarily, we're only really allowed to do a few operations. And the key operations here are that we can put an object, we can get an object, we can delete an object, and finally, we can list objects. It should feel somewhat limited because these limitations are in part of why we actually get the scalability that we do with object storage. So it's not as simple as just adding a new API. Further, if you think about how you actually delete a file on some file system, so pretend you were SSHing into another server. Typically what you do is you actually list the files and then you figure out what you want to delete. But in this system with object storage, it's actually a little challenging because you don't have the hierarchy anymore to help you do lists efficiently. There are ways around it and there are optimizations, but it remains a fundamental limitation. Additionally, there's also this question of what exactly a partial deletion means. If I want to delete one row, you can notice here that I'm using this word object, which is really just a bunch of bytes. It's not a specific table, and there's no defined exact way in an object store to delete just a portion of something. There's no real definition of what that means. So you can already kind of tell that this concept of a row level delete is starting to get a little hard. And to spoil some of the surprise, the way we get around a lot of the limitations with object storage is via this thing called Iceberg. I don't know if anyone's heard of it in this room, but it's this system where we have a tree-like metadata structure to track data files over time. Okay, no one reacted when I said, I don't know if anyone's heard of it, but I think everyone raised their hand when Chan asked. So someone definitely knows. So hopefully this looks familiar, where we have this Iceberg catalog that stores the current metadata pointer, and then we're able to access all of our Parquet data and delete files to do our actual reads. And this unlocks a lot of great stuff like asset guarantees, scalability, APIs, and especially row-level deletes bolded here. So given all this context of why this might even be a problem, let's go back to Hive and talk a little bit about Hive did deletes. And the short answer here is I didn't really do deletes. What do I mean by that? It means that if you want to delete a given row, you end up deleting the entire partition. And it's very common that you partition your data actually by dates. And so it becomes a problem where you end up having to drop an entire day just to delete one record. And for many business use cases and use cases in general, this is unacceptable. And so you're forced to end up recomputing the entire partition of what it should be yourself so you can drop it, figure out the new partition, and then add the new partition in yourself. I'm seeing some heads nod. If you've ever done this, it's very painful. And to give you an idea of just how painful, we can take a look at all the steps that are required, where you basically do exactly what I described. And to make things even better, this is not ACID compliant, which means that if you have any concurrent jobs accessing a given partition where one is deleting something and another is inserting, you have signed yourself up for 12 hours of no sleep. It's worse than on-call, and it's a terrible experience. So given all of this context, Iceberg v1 now steps into the picture. And we introduce this concept we call copy on write. The key idea here is that we're going to address the deletions by just generating a new copy of the data file without the deleted rows. Now, this will also be ACID compliant because we're going to leverage the Iceberg commit pattern where we generate all of our data files or /delete files as needed. But we haven't got to the delete files yet, but you can pretend it's part of the same commit structure. And then you generate all of your metadata. And at the very end, at the last step, you try to go to the catalog and do an atomic commit. So you don't run into these issues where multiple people are trying to access the underlying same data files, because it's actually very rare to actually delete a file directly. Let's do an example of how copy on write works. Let's say I have some arbitrary table, and we're just looking at the first 5 rows within this. If I want to run a command to delete rows 2 and 4, I simply generate a new copy of this file without those rows. And this new file gets saved and tracked in the latest Iceberg metadata version, and I do the update via the catalog. The problem is that we're rewriting this new file and we're invalidating the old one, which is pretty expensive. If we think about how this scales with the size of the actual table that you're deleting. It doesn't scale with the number of deletes that you have. And so if you have a lot of records and tables, which is very common because the whole point of doing this is for really large scale storage, you start to run into performance related issues and compute related issues. So now we go to the next step, Iceberg v2, which tried to address this with the concept of positional deletes. The way that we address this is something called merge on read. The key idea here is that instead of generating a new file like we did with copy on write, we're just going to store the deletions as a file directly. Iceberg v2 has two different variations of Parquet delete files. The first one is called positional deletes. The idea here is that you calculate what positions in a given file you want to skip. The alternative is an equality delete, where instead of calculating the position at write time, you instead generate a more broad category. For example, maybe where ID equals 5. And in that scenario, at read time, the engine then has to do the work of taking this equality delete file and figuring out where to delete. So the trade-off here between the read and write time, that Iceberg gives you the flexibility to decide how you want to represent your deletes. For the purposes of this talk, I'm going to focus on positional deletes, just because that's the one that we've evolved into deletion vectors. Equality deletes remains the same and is unchanged in Iceberg v3 compared to Iceberg v2. Like I did with copy on write, I'm not going to do an example of how merge on read works. Let's say, again, we start with a table, the exact same table, and we focus again on the first 5 rows. We're going to run the same delete operation on rows 2 and 4, and this time, we create a new positional delete file. To be very specific, it is a Parquet delete file, which is going to be relevant soon. And this way, we can now track the deleted rows, or the indexes of 2 and 4. When we now go to read, we then see this, where we see the original table, we then see the delete file, and then the engine merges them at read time, hence the name merge on read. And then we just skip rows 2 and 4, hence why they're annotated as being deleted. This leads to no rewrites, and we also have 2 ways to group these positional deletes. The first one is we can scope them at the partition level, which means I create one file for all of the given deletes that affect a given partition. And the alternative is a file scope delete, which is now the default in Spark 3.5 and the latest Iceberg 1.8 that targets Java. The issue, though, is that now there's a trade-off on the number of delete files you have. As you can imagine, merge on read makes this trade-off where we're delaying the cost of the rewrite, where now on read time, you have to account for all these delete files. And if you have one per every single file, and maybe you're doing a bunch of different deletes, you start accumulating a lot of really tiny files. And they start adding up and imposing an IO tax and penalty every single time you want to make a read on these tables. So to solve that, typically you do compaction, where you take a bunch of these small delete files and you create a big delete file, or you might as well just combine the actual delete files with the old large Parquet file and effectively run a copy on write every once in a while. And that improves your performance going forward. I've spent all this time talking about how the Parquet delete file works, but it turns out that engines don't actually understand the Parquet delete file directly, and the engine level representation is actually entirely different. Let's start from the basics. There's this concept of a bitmap, where we're going to go ahead and store a bunch of indexes by using a map of bits that correspond to those indexes. So it's very useful for bitwise operations, which is why we're going through all the penalty and the stress of trying to figure out this kind of operation, where if I want to union or do any intersections with sets, it's very simple because you can just do it bitwise. And a lot of processors and computational techniques these days are optimized for those kinds of operations. Here's an example of what that would look like, where you have a bunch of indexes laid out, and you have a bitmap where one corresponds to indexes 0, 2, and 4. And so what that means is that those are now existing in this given set. We then take this a step further, and we introduce this concept of roaring bitmaps, where the idea is bitmaps are really space intensive. If I want to store a bitmap for 0 to any n, I have to store a bit for every single number, even if all the numbers are 0, which means that there's no deletes. The problem with that is you start spending a lot of unnecessary space on these bitmaps, even if they're super great because of these bitwise operations. And so this concept of the roaring bitmap came into play, where we're now going to start playing around a little bit. We're going to say we have some 32-bit number, and we're going to start chunking them. So we're going to chunk it apart into 2 pieces. The first, we're going to take the most significant 16 bits. So these are the 16 bits on the left-hand side of the number, and we're going to call this some key. And then we're going to take the remaining 16 bits and group these all into containers by the key. The idea here is that we can actually leverage the cardinality, which means the number of unique elements in a given set, on the container, and then we can figure out the best kind of container to use. So the key idea here is that we're going to use bitmaps when it makes sense, and when it doesn't make sense, we're just going to use arrays. And then we also have this other concept of what's called a run. A run is a group of consecutive numbers. I have an example that goes through this, but the run length encoding is actually very important to prove that roaring bitmaps are the best way to compress these kinds of numbers. It's actually a paper that goes through a lot of detail. The original paper doesn't include the run length encoding and is like, I want to say like 10 pages long. And then they introduce it and it jumps to like 25 pages and it's like the same underlying topic. So the actual bitmap is just a bunch of numbers like 1, 0, 1, 0, 0, so on and so forth. Then we throw in our sorted array. This is the classic way to just represent a bunch of indexes together. This is the alternative where you don't have a lot of cardinality. And then the third option is this run length encoding, where if I have some numbers like 11, 12, 13, 14, I can just encode that as 11, 3, and it does the same idea. So I've spent all this time talking about roaring bitmaps and the engine level representation, and it sounds nothing like what I talked about with the Parquet delete files. And if that's what's going through your mind, you're exactly correct. We have this representation mismatch between what's happening in the engine and on disk. So engines use the roaring bitmaps. And the reason is, like what I was talking, you get all these great benefits of this set-like operations done bitwise, which allows you to vectorize your operations across many rows of data at once. However, it's different than how deletes are stored on disk as your Parquet delete files. And so your engine ends up playing this game where it's playing catch between your disk and your memory on all these given writes and reads, and it imposes a penalty and an overhead every single time. And you might be asking why. Why would anyone choose to ever knowingly make this decision and like approve the Iceberg v2 spec? Well, the honest answer is we're now going to get a little bit more deeper into the details and talk a little bit about how we're going to implement this for 64-bit numbers, which wasn't clearly defined at the time, and it was only defined for 32-bit numbers. So instead, the Parquet delete file was chosen because Parquet is a format that can be read by any engine. So there's no issue with how you're actually saving the serialization of the binary blob that compromises the roaring bitmap. That's a handful of words. The key idea that I want everyone to take away from this is just that there's a representation mismatch. What you save on disk is different than what the engine needs. With that, let's now go into the third phase of Iceberg v3, deletion vectors. So I want to start by highlighting what are the key problems and how we're going to improve this to like give almost a forecast of what we're about to discuss. The first one is what I just talked about, this overhead due to the difference between on-disk and in-memory representations. The second one was about the trade-off between file scoping and partition scoping, where it affects the number of delete files you have, but then also with the partition scoping, you're loading delete files that may not be actually relevant to the files that you're trying to read. You just happen to be accessing that partition, and now you pay the penalty of loading everything. And then finally, we also talked a little bit about this maintenance procedure, where you have to compact your delete files to avoid there being too many. And there's some issues with that because the maintenance procedures are entirely optional, which means that you may run into scenarios where it may not be optimal to have that many delete files. So to solve these, Iceberg v3 introduces a couple improvements. The first one is this concept of using the roaring bitmap for both on-disk and in-memory representations, which addresses our issue with the overhead and difference between the representations. The second one is we're going to use file scoping for all delete files. This one sounds a little weird because it feels like we could have just done that in Iceberg v2. Like there's no reason why not. And I hear you saying, well, okay, the problem with that was we had too many delete files. And so what we're going to do with this third thing is we're actually just going to force synchronous maintenance on write. And so we're going to shift the burden onto the engine when it's doing the write to compact these delete files together so that you can guarantee that there's one deletion vector per file per snapshot going forward to ensure good performance. Let's now construct a deletion vector and actually understand what's happening at the binary level of the blob. So our goal here is to store a non-negative 64-bit number in some bitmap. We can optimize actually for 32-bit positions and leverage the 32-bit roaring bitmap that was clearly defined by splitting again the first 32 bits into a key and then using a roaring bitmap for the second 32 bits on the subpositions. The idea for why this is useful and why we don't just use a 64-bit roaring bitmap directly is that the expectation is that most of your numbers will be inside where all of the key is going to be 0. With 32 bits is a lot. 2 to the power of 32 is a very, very big number, and it's hard to get to that many indexes consistently. So this allows us to save space, but gives us the flexibility to add more bitmaps if we ever need to. So we start out with some length. This is the first 4 bytes within our blob. We then introduce some magic bytes. We then actually do the roaring bitmap, and we call this the portable format to explain the fact that we're accounting for 64 bits and not 32. And then finally, we have some checksum to just verify that we have the right bytes. And then additionally, expanding on that, we have some arbitrary magic bytes that I've isolated here if you're curious. And then we actually have the roaring bitmap, where you can see that we have this key setup of 4 bytes, which is the first 32 bits. And then we actually have the bitmap in however much space we need based on how the roaring bitmap ends up working. We also store the number of 32-bit bitmaps, which is useful if we, for some reason, violate that earlier assumption and our keys are not just all zeros, and we actually have a lot of numbers. We are flexible enough to account for that. So this is the deletion vector blob. This is the actual binary ones and zeros that are on disk and in memory. The way that we actually store them, though, in Iceberg is via this nice thing called a puffin file. So puffins are great because they can store arbitrary blobs and things that don't really make sense to go inside the Iceberg metadata manifest tree. So these just contain arbitrary information, and one of the great things that they contain is this thing called the deletion vector v1 blob type. And so very similar to what we just saw, we're now stacking all of the deletion vector blobs on top of each other. There's a footer at the bottom which includes some information about where exactly to go if you want to access some deletion vector. And it also tells you what data file it references and the cardinality of how many indexes are included within that deletion vector roaring bitmap. You'll notice also that the same deletion vector blob that we talked about on the previous slide is what we're stacking up on top of each other. So now we're starting to build the pieces, and there's one more final piece that we have to build, which is the actual delete manifest that now goes inside the Iceberg metadata tree. And the reason why we want this is because we want to use this as a pointer to go exactly to the deletion vector blob. We want to avoid this issue that we had with partition scoping, where we load the entire puffin file and then have to find our deletion vector. Instead, we're able to leverage the delete manifest and go to the correct position inside of our puffin file to get the roaring bitmap that we want. So we again have our dvs.puffin file that includes all of our blobs stacked on top of each other. And then we have some delete manifest, typically in Avro, where we have some contents and some file paths, and it tells us where to go to get our actual deletion vector. And the nice thing is that when you go via this actual this delete manifest, you'll have these arrows that tell you exactly where to go to get your blobs, so you can avoid having to go into the footer of the puffin file and then jump around to find what you need. It's a small optimization, but it's one that matters a lot. And this is what goes inside the Iceberg metadata tree. So when your engine's trying to access a roaring bitmap, it follows this path. I now want to start talking a little bit about how that maintenance procedure works now that we've actually built up the actual deletion vector blobs. In Iceberg v2, engines got to choose when they're going to compact delete files. But the issue is that compaction is always an extra cost incurred by an engine, and it's sometimes hard to justify because it's not directly related to a current write that's happening. So it makes sense that sometimes you're going to try to push that off for as long as you can and hope that it happens. Iceberg v3, though, enforces that you have at most one deletion vector per data file per snapshot, which is now a write time requirement to ensure good performance going forward. And the nice benefit of this is that Iceberg v2 position deletes now have an easy path to be upgraded, where Iceberg v3 can read those Iceberg v2 position deletes, but once you write something with an Iceberg v3 writer, it'll go back, find all your positional deletes, combine them, and then give you one nice deletion vector blob to use going forward. So it's a nice almost migration path if you really think about it. So I'm going to now go through an example of how this works, because I realize that this sentence, at most one deletion vector per data file per snapshot, gets a little confusing when you start thinking about time travel and you want to account for different deletions at different moments in time, but still make sure that they are valid. So we start out with creating some file with a number of rows without any DVs. We then create another snapshot where I'm going to delete ID equals 1. We create some deletion vector. I'll call this dv1. That is just storing ID equals 1 inside of the roaring bitmap, probably using some array because there's so few. We then go ahead and add ID equals 5. Technically, this would create a new Parquet data file and it really made the diagram complicated. So I'm just going to pretend like we just added into the original table. And 1 still remains deleted using the original deletion vector. And this is the key part where now we delete ID equals 4. And now in Iceberg v3, when we delete ID equals 4, we create a new roaring bitmap stored in this new deletion vector blob that contains both 1 and 4. Iceberg v2 would have only contained 4, and then you would have to go through and figure out ID equals 1, ID equals 4, and do the work yourself of having multiple delete files. So if you take a look at this, we're able to time travel. So I could go back to snapshot 1, snapshot 2, read the table at those moments in time. But at any moment when I'm trying to actually read the table, there's only one deletion vector blob that I actually care about. And so we're able to hit our performance requirement and still be fine. And then finally, oh, that's a scary word, delta lake, inside the Iceberg talk. One thing that's worth calling out with the deletion vector blob is that the formats, we believe, should not silo data. And as a result, delta actually uses the same binaries for the deletion vectors. So it actually goes down to the exact like ordering of the bytes, right? Where we use big endian values for length and the checksum fields, as well as little endian values for the actual roaring bitmap itself. That's a little handshake going on. So I want to conclude this talk, I think I'm about a minute over, just talking a little bit about the summary of deletion vectors that we discussed at this talk, just because we've discussed a lot of things. And if I have to leave you with anything, it's just these 4 things, where we started out with our Hive style deletes, where you dropped and you added a replacement partition and did your best to figure out what should be deleted. We then went to this copy on write method, where you rewrote the Parquet data file without the deleted rows. Then we went to this position delete method, where you write the Parquet data files, partition or file scoped. And then we finally concluded with Iceberg v3, where we're now going to use roaring bitmaps directly and enforce compaction to solve some of the problems we ran into. And we encourage you to join the Iceberg community today.
Cool. That was very interesting. Does anybody have any questions? Oh, of course.
Hopefully these questions aren't too hard.
Going back to your previous slide with the 4, what were the magnitudes of performance improvements that you would see going from each?
Yeah, so that's a good question about like what the magnitude of performance like improvements you would see across each. So going from Hive to like anything else is huge. When you go from Iceberg, so to be very clear, the copy on write method is still supported inside Iceberg v2 and Iceberg v3. The difference is that most of your workloads are not going to be like deleting enough files to the point that like you want to have copy on write as your default. It's often better to set deletion vectors or Parquet delete files as your default. You can think about it as like a reasonable improvement on most workloads, especially on like you can think about it almost as like your like BI workloads, where maybe like you're deleting a few rows at a time. You're going to see like a very noticeable improvement. If I'm being totally honest, the representation is like kind of a small overhead because most engines can kind of figure out how to make that transition, especially once you actually load the data file and you start doing your operations in memory. You really start to notice the translation between on disk and like the in-memory representation with the bitmaps only when you're actually persisting files. So if you're just doing a bunch of operations in memory, you won't actually notice that difference. So the difference decreases. I said a lot of words. The simple way to think about it is as you go down, the order of magnitude decreases.
So the puffin files you talked about here, is it different from, I think earlier there was a stats related puffin files as well, right? So those are 2 different things here, like that gets written to a metadata folder.
I have no idea what you're talking about
The,
with
I think
stats file.
there's the S3 Iceberg table that creates a stats and then stores a puffin files.
I don't know anything about S3 tables, and I'm not an authority to speak on that.
It's an Iceberg table with puffin files.
That stats files is it same or is it different?
Yeah. Well, so to clarify, Puffin is just like an Iceberg like file type that's used to score. It's technically called a sketch, which is like just like information that's like broadly useful across like a bunch of files. I want to clarify that I'm not saying like I don't want to make a statement that is specific to how S3 tables works, that it does or does not support that, because I'm not familiar with any such limitations or guarantees that S3 tables offers. I feel like I'm like at a press conference, just like being like very like precise.
A little bit. Okay, I'll take one more.
Thanks for the great talk. So performance of the V3 looks lucrative, right? But is this a one-way door, the migration from V2 to V3?
Yes. So there's backwards compatibility in the sense that Iceberg v2 deletion like files can be read in Iceberg v3, but there's no forwards compatibility in the sense that once you write a roaring bitmap, the Iceberg v2 engines will not understand what that is, even though it's funny because the actual engine understands it. So it's kind of a weird thing.
So basically, let's just theorize, right? So I'm using the V2 and then I want to move to V3. So I move all my, say, writers to V3. So I have a puffin files from now on. And then say, from this time, I need to make sure that all my, like, say, whoever uses Spark to write that has the V3 support on. Otherwise, it's going to be not supported. Because the way I understand it, like the Athena, Trino, they already do that. They already support puffin files. But like, arbitrary Spark job that I'm running should support it. Otherwise, I won't be able to read it, right?
I think I follow that. I want to like restate in my own words just to make sure. So if you have some writer that is now Iceberg v3, let's say you had like a bunch of tables that are all Iceberg v2, the first time you commit a write using an Iceberg v3 writer, on that snapshot, it will go ahead and create a new deletion vector blob. So even if you understand the puffin file format, you need to make sure that all of your readers understand the deletion vector v1 blob type that can be stored inside of a puffin file, which is a slightly different thing that is adjacent to the puffin file understanding, right? Like I can understand a puffin file, but then if a new type like deletion vector v2 or v3 or something was added as a blob type, I may not understand that. So basically what I'm saying is once you write to it with an Iceberg v3 like writer, you need to make sure that anything that's reading it has support to understand the deletion vector blobs, and then you're good going forward. I would encourage you to think about it as like the deletion vector blob requirement and less about the puffin requirements. Okay, thanks everyone.
Thank you. Okay, cool. I just have two more things to say. Thank you everybody for staying. I want to give a huge shout out to all of our co-hosts. We have Dremio, Snowflake, Graybeam, Databricks, AWS, and Stellar Data. Stellar Data brought some really cute t-shirts, so go check them out. Okay, here's the QR code again. If you haven't scanned already, do it now. Anybody? No? Okay, fine. We're hiring. So careers@eventualcomputing.com. If you want to be in this beautiful picture, email us. And then lastly, join our Slack. And then if you want to try out Daft, literally pip install get Daft and it should work. I mean, it will work, not should, it will work. Join our Slack. We're always on there. Ask us questions. Do I have any more slides? No, that's all. Okay, that is the end, but stay. We have so much pizza left. We have a lot of drinks left. Stay, network, chat, whatever you want. Thank you guys for coming.